5,000 years before the telescope was invented, ancient civilizations were tracking planets with precision that rivals modern astronomy. The Babylonians predicted eclipses centuries in advance. The Maya calculated Venus's orbit to within hours. The Egyptians aligned monuments to celestial coordinates with accuracy we can barely achieve today. How did they do it? Popular theories claim aliens, lost technology, or supernatural powers. But the truth is far more extraordinary and far more human. Ancient peoples achieved astronomical mastery through patient observation, mathematical genius, and a profound connection to the night sky that modern civilization has lost. What they accomplished without computers, without telescopes, without even basic optics, challenges everything we think we know about primitive cultures. By the end of this video, you'll understand how ancient astronomers decoded the cosmos using nothing but naked eyes, clever mathematics, and centuries of careful record-keeping. And you'll discover why their achievements terrify modern scientists who realize how much knowledge we've actually lost. Hit subscribe. This journey through ancient astronomy will blow your mind. Before we explore what ancient civilizations knew, we must understand something profound. They saw a completely different night sky than we do. The dark sky advantage modern humans live under light pollution. 80% of the world's population can't see the Milky Way from where they live. Major cities have skies 100 times brighter than natural darkness. We see maybe 200 to 300 stars on a clear night. Ancient peoples saw 2,000-3,000 stars with the naked eye on clear nights, the Milky Way as a brilliant river of light stretching across the sky, planets moving against the stellar background with crystal clarity. Subtle celestial phenomena we can only detect with instruments. The motivation: why did ancient civilizations care so much about astronomy? The sky was their calendar, tracking seasons for planting and harvest, clock, telling time at night through star positions, compass, navigating by celestial references, weather predictor. Certain celestial events correlated with seasonal changes, religious connection. The heavens were the realm of gods. The observation method: ancient astronomers used sophisticated techniques. Horizon markers, stone monuments to track sunrise/sunset positions over the year. Sighting tubes, hollow reeds or tubes to focus attention on specific stars. Water basins, still water reflecting stars to measure positions and movements. Plumb lines, weighted strings to establish vertical references. Shadow clocks, tracking sun position through shadow movement. Star lists, careful recording of star positions over decades and centuries. The key insight: ancient astronomy succeeded because observations were made over centuries by professional priest astronomers. Data was carefully recorded and transmitted across generations. Mathematical patterns were identified and systematized. Cultural importance ensured resources and prestige for astronomers. If the idea that ancient people understood the cosmos as well as modern scientists fascinates you, drop a like. Their achievements are mind-blowing. The oldest systematic astronomy comes from Mesopotamia, the land between the Tigris and Euphrates rivers, where the Sumerians and later Babylonians created civilization's first star catalogs. The mul.appin tablets dating to approximately 700 BCE, but copying earlier observations from 1000 plus BCE. The mul.appin contains a catalog of 66 stars and constellations, rising and setting times throughout the year, the path of the moon through constellations, planetary movements, and periods. Eclipse prediction methods: a 12-month lunar calendar with intercalation rules. The 3 stars each. Babylonian star lists organized the sky into 3 ways: Way of Anu, equatorial stars, way of Enlil, northern stars, way of Ea. Southern stars. Each way contains stars associated with specific gods, months, and seasonal activities. Eclipse predictions: the Babylonians discovered the Saros cycle. Eclipses repeat in patterns every 18 years, 11 days, 8 hours. This 223-month cycle allowed predicting eclipses centuries in. Advanced Babylonian eclipse predictions survive on clay tablets. They were astonishingly accurate to predict eclipses. Babylonians developed base 60-number system, still used today for time and angles. Sophisticated arithmetic for astronomical calculations, understanding of lunar nodes, where Moon's orbit crosses ecliptic, recognition of planetary periods and synodic cycles. Venus observations, the Venus tablet of Amasuduka, circa 1600 BCE, records Venus's appearances and disappearances over 21 years. Shows Venus's 584-day synodic period connects celestial events to earthly omens, demonstrates systematic long-term observation. Planetary periods, Babylonians calculated planetary synodic periods with remarkable accuracy. Mercury, 115.9 days, modern, 115.88 days. Venus, 583.9 days, modern, 583.92 days. Mars, 780 days, modern, 779.94 days. Jupiter, 398.9 days, modern, 398.88 days. Saturn, 378.1 days, modern, 378.09 days. These values are accurate to within 0.1%, achieved through patient observation and mathematical analysis over centuries. The astronomical diaries from 700 BCE to 50 CE, Babylonian astronomers maintained astronomical diaries, daily records of celestial phenomena, weather conditions, market prices, and historical events, creating a data set spanning 650-plus years. This continuous record-keeping allowed identifying long-term patterns, developing predictive models, creating mathematical astronomy, laying foundations for Greek astronomy. How they did it. Babylonian methods. Professional astronomer. Priests maintained observational programs, observations made from ziggurat tops, elevated platforms, systematic recording on clay tablets, durable medium, institutional support, ensuring continuity, mathematical tools for pattern recognition. The Egyptians took astronomy from observation to architecture, encoding celestial knowledge into stone monuments that have lasted millennia. The Pyramids of Giza. The Great Pyramid demonstrates astronomical sophistication that baffles modern engineers. The pyramid's sides align to true north with extraordinary precision. Deviation from true north, 3/60th of a single degree more accurate than the Royal Observatory at Greenwich. When it was built, this precision maintained across a base spanning 13 acres. How did they achieve this? Method 1. Circumpolar star observations. Track a circumpolar star as it circles the north celestial pole. Mark its highest and lowest positions. Bisect the arc between these points. This gives true north. Method 2. Indian circle method. Create a level circular platform. Mark shadow positions throughout the day. The bisector of morning and afternoon shadows points north. The pyramid shafts from the king's chamber align with northern shaft, pointed at Thuban, Alpha Draconis. The pole star circa 2500 BC. Southern shaft, pointed at Orion's belt stars from the queen's chamber. Southern shaft aimed at Sirius. These weren't accidents. They were deliberate astronomical alignments at Orion's belt connection. Robert Bauval's Orion correlation theory. Controversial but intriguing. The three Giza pyramids layout matches the three belt stars of Orion. The air shafts point to Orion, associated with Osiris. The Nile's position corresponds to the Milky Way. The solar calendar. Egyptians developed a 365-day solar calendar, 12 months of 30 days plus 5 extra days, epigomenal days, used for administrative and agricultural planning. One of humanity's first solar calendar. Sirius rising. The heliacal rising of Sirius, Sopdet, marked the beginning of the Egyptian year. Coincided with the Nile's annual flood. Occurred around July 20th in ancient times. Allowed predicting the flood season. This shows Egyptian astronomy was practical. Tracking Sirius equals predicting floods equals planning agriculture. The sky was a cosmic calendar governing earthly cycles. The Dendra zodiac, the ceiling of Dendra temple, contains a circular star map showing constellations, planetary positions. Decans, 36 star groups used for timekeeping. The zodiac, showing Greek influence in Ptolemaic period. The shadow clock and water clock. Egyptians measured time using shadow clocks, sundials tracking sun position by shadow length. Water clocks, clepsydra, water dripping at constant rate to measure night hour. Star tables and decans. Coffin lids and tomb ceilings display diagonal star tables. 36 decans, star groups rising 10 days apart. Each decan marks a 10-day period together, covering the full Year used to tell time at night by watching which decan was rising. The sophisticated understanding Egyptian astronomy shows. Precise cardinal alignment techniques, long-term observation of Sirius and other stars, integration of astronomy with architecture, use of the sky as a practical tool for timekeeping and agriculture, understanding of annual celestial cycles. The precision of the Great Pyramid's alignment, 3/60th of a degree off true north, built 4,500 years ago, is staggering. How do you think they achieved it? Share your theories in the comments. The Maya developed arguably the most sophisticated astronomy of any ancient American civilization, creating calendars and predictions that rival modern precision. The Dresden Codex, one of 4 surviving Mayan books, the Dresden Codex contains detailed Venus tables, eclipse prediction tables, ritual calendar correlations, mathematical astronomy calculations. The Venus table: the Maya tracked Venus with obsessive precision. Synodic period of Venus, 583.92 days. Modern value, 583.92 days. They calculated this. Over centuries of observations, the Dresden Codex contains Venus tables spanning 104 years, predictions accurate to within 2 hours over this period. Why Venus mattered. Venus was associated with war and sacrifice. Heliacal rising, first appearance before dawn, was especially important. Warfare and rituals were timed to Venus events. The morning star and evening star phases had different meanings. The calendar system: the Maya actually used multiple interlocking calendars. 1. Sokin, 260-day ritual calendar, 13 numbers times 20-day names used for divination and ritual timing, origin possibly based on human gestation. 9 months is almost equal to 260 days. 2. Hab, 365-day solar calendar, 18 months of 20 days plus 5 unlucky days, tracked seasonal and agricultural cycles. Similar structure to Egyptian calendar. 3. Long count, linear count of days from mythological creation date, August 11th, 3114 BCE in proleptic Gregorian calendar, allowed dating events across vast timespans, famous for the 2012 end of the world completion of a BAK-ton cycle. The calendar round, the Tsokin and Hab mesh like interlocking gears, creates a 52-year cycle, 18,980 days. After 52 years, the same date combination repeats. This calendar round was ceremonially significant. Eclipse predictions: the Dresden Codex contains eclipse tables, covers a 33-year eclipse cycle based on the 173.31-day eclipse season, lists potential eclipse dates with warning glyphs, shows understanding of lunar nodes and eclipse mechanisms. The Venus-Jupiter conjunction: Maya texts record precise observations of Venus-Jupiter conjunctions. These occur approximately every 2 years. Maya tables predict them across centuries, used for ritual and political purposes. Architectural alignments: Mayan buildings encode astronomical knowledge. El Castillo, Chichen Itza, 91 steps on each of 4 sides plus top platform equals 365. Equinox shadow creates serpent descending stairs. Windows align with Venus extreme positions. Governor's palace, Uxmal aligned to Venus southernmost rising point, demonstrates long-term observation of Venus's 8-year cycle. How they observed Maya astronomical methods: observation from tops of pyramids, elevated view, crossed sticks creating sighting lines, zenith tubes, vertical tubes to observe stars crossing directly overhead, patient multi-generational record keeping, mathematical pattern analysis. The mathematical foundation: Maya mathematics was sophisticated. Base 20 number system, concept of zero, independently invented. Positional notation allowing large number calculations used for complex astronomical calculations. The achievement Maya astronomy demonstrates extraordinary observational patience, centuries of data, mathematical sophistication, integration of astronomy with architecture and culture, predictive models accurate across decades. Long before the Maya, before the Egyptians, Neolithic Europeans were encoding astronomical knowledge into massive stone monuments. Stonehenge, the stone observatory built in stages from 3000 to 1500 BCE. Stonehenge is fundamentally an astronomical instrument. The solstice alignment, the monument's most famous feature. The avenue and main axis align to summer solstice sunrise on midsummer morning. The sun rises directly over the heel stone viewed from the center. This creates a dramatic spectacle. Winter solstice sunset aligns in the opposite direction. The alignment is accurate to within half a degree, maintained across a structure built over 1,500 years. The lunar standstill, the moon's orbit is complex, rises and sets at different points along the horizon over an 18.6-year cycle. These points reach extreme. Stonehenge station stones mark these lunar extreme points. The Aubrey holds 56 pits around Stonehenge's outer circle. Their number might relate to eclipse prediction 3 cycles of 18.67 years. Lunar node cycle equals 56 years. Moving markers between holes could predict eclipses. This interpretation is debated but intriguing. Newgrange. The winter solstice chamber in Ireland. Newgrange predates Stonehenge by 500 years. Built around 3200 BCE, contains a roof box aligned to winter solstice sunrise for 17 minutes at dawn on the solstice. Sunlight penetrates 60 feet into the chamber, illuminates the back wall with golden light. This effect requires precise understanding of solar movements, careful architectural planning, multi-generational commitment to construction, astronomical knowledge dating back 5,200 years. Callanish standing stones, Scotland. Complex megalithic site with multiple alignments. Main avenue aligned to southerly moon setting during major standstill, cross-shaped layout with astronomical significance. Various stones aligned to different celestial events. Carnac stones, France. Vast field of over 3,000 standing stones, arranged in rows stretching over 4 kilometers. Some researchers suggest solar alignments. Others propose lunar orientation. Function remains debated but clearly involved astronomical observation. Who built these? The societies that created megalithic observatories were Neolithic farmers, not primitive hunter-gatherers, had surplus resources to invest in monument construction, possessed sophisticated mathematical and astronomical knowledge, maintained long-term cultural memory across generations. Why build them? Motivations for megalithic observatories. Agricultural. Calendar, when to plant/harvest. Seasonal timekeeping, predicting weather patterns, connecting earthly and celestial realms, marking sacred times, honoring solar/lunar deities, demonstrating power and knowledge, creating community gathering places, establishing territorial markers. The construction mystery. These monuments required moving multi-ton stones long distances, precision placement for alignments, coordinating labor of hundreds or thousands, maintaining architectural vision over generations. The legacy. European megalithic astronomy shows advanced astronomical knowledge existed in prehistory. Complex societies thrived before written record. Stone encoding allowed preserving knowledge across millennia. Human ingenuity finds solutions with available technology. The cultures we've explored aren't alone. Around the world, ancient peoples independently developed astronomical sophistication. Ancient China. Chinese astronomy dates back thousands of years. Earliest supernova records. Chinese astronomers recorded guest stars, supernovae, as early as 1054 CE, Crab Nebula. Eclipse records. Systematic observations dating to Shang Dynasty, 1600 to 1046 BCE. Planetary observations. Detailed records of planets, comets, and meteor star catalogs. Sher Shun's catalog, 4th century BCE, listed 800-plus stars. Antikythera mechanism. Greek astronomical computer, c. 100 BCE mechanical device with 30-plus bronze gears, calculated astronomical positions and eclipses, predicted planetary movements. Shows Hellenistic astronomical knowledge encoded in physical technology. Polynesian navigation. Pacific island navigators crossed thousands of miles of open ocean. Memorized rising/setting positions of hundreds of stars. Used star paths for navigation. Tracked seasonal changes in star positions. Navigated without instruments across vast ocean distances. Chaco Canyon, ancestral Puebloans. Southwestern United States sites show astronomical alignments. Buildings oriented to solstices and equinoxes. Possible lunar standstill observations. Sun daggers marking seasonal events. Integration of astronomy into architecture. African astronomy. Nabta Playa, Egypt. 7,000 years ago. Stone circle aligned to summer solstice. Possible megalithic calendar. Predates Stonehenge by 1,000 years. Dogon, Mali. Traditional knowledge of Sirius star system controversial. Claims about Sirius B, invisible to naked eye. Debate whether knowledge is genuinely ancient or modern. Contamination. Indian astronomy. Ancient India developed sophisticated astronomy. Vedanga Jyotisha, 1400 BCE. Contains astronomical calculations, understanding of planetary periods, development of trigonometry for astronomical calculations. Later work by Aryabhata, 499 CE, calculated planetary positions with precision. Common patterns across cultures. We see solstice and equinox observation. Tracking of Venus and bright planets. Development of calendars. Eclipse prediction attempts. Integration of astronomy with religion and agriculture. The question that haunts modern observers: how did ancient civilizations achieve such precision without our tools? The advantages of patience. Ancient astronomers had something we don't: Time. A modern astronomer has a 30 to 40-year career in ancient astronomical tradition span centuries. Knowledge was institutionalized in priesthoods. Each generation built on the previous one's work, the power of dark skies without light pollution. Celestial phenomena were dramatically visible. Subtle motions became apparent overnight. Weeks. Pattern recognition was easier. The sky commanded attention and respect. Simple but effective tools. Ancient astronomers used basic instruments with sophisticated techniques. Sighting sticks. Two aligned sticks create a fixed sighting line to track star positions over time. Plumb lines establish vertical reference for measuring angle. Shadow clocks track sun position through shadow length and direction. Water levels create perfectly horizontal surfaces for measurement. Stone markers, permanent horizon markers for tracking rising / setting positions. Cross sticks create precise alignment for observing specific celestial positions. Record keeping. The real secret was systematic documentation. Clay tablets, Mesopotamia. Durable records lasting millennia. Stone inscriptions, Egypt. Permanent celestial data codices, Maya. Illustrated astronomical tables. Oral tradition, Polynesia. Memorized star paths and celestial knowledge. Mathematical sophistication. Ancient mathematicians developed number systems suitable for astronomical calculations. Geometric principles for understanding celestial spheres. Arithmetic for predicting planetary positions. Pattern recognition for identifying cycles. The observational method. How to track planets without telescopes. Select bright reference stars near a planet's path. Observe the planet's position relative to these stars. Nightly record the positions systematically over months / years. The planet's motion becomes clear. Identify periodic patterns in the data. Develop mathematical models to predict future positions. Test predictions against new observations. Refine models based on discrepancies. Why we couldn't do it today? Modern humans would struggle to replicate ancient astronomy because we lack the dark skies, light pollution. We lack the patience, careers are short. We lack the cultural motivation, practical needs met by technology. We lack institutional support, no royal astronomers or priest astronomers. We've outsourced sky knowledge to instruments. The humbling truth: ancient astronomers succeeded through observation, not technology. Patience, not processing power. Mathematics, not machinery. Human ingenuity, not supernatural intervention. Could you track Venus's position for 40 years with just your eyes and a notebook? Ancient astronomers did exactly that across generations. What does this say about human capability and patience? Share your thoughts in the comments. Ancient astronomical achievements reveal an uncomfortable truth. Our ancestors weren't intellectually inferior to us. They were every bit as smart, observant, and capable as modern humans. What they accomplished without telescopes, without computers, without even basic optics, ancient civilizations tracked planetary motions with precision. Matching modern measurements. Predicted eclipses centuries in advance. Calculated planetary periods accurate to 0.1%. Aligned monuments to celestial coordinates with extraordinary accuracy. Developed mathematical models that worked across centuries. Created calendars more accurate than those used in medieval Europe. Why this matters: understanding ancient astronomy correctly is important. Attributing ancient achievements to aliens insults the intelligence and capabilities of our ancestors. Denies the genuine human genius that created these achievements. Misunderstands how patient observation and mathematics work. Perpetuates racist narratives about primitive peoples. Ancient peoples achieved astronomical mastery through generations of patient observation. Institutional support for astronomical programs. Mathematical sophistication and pattern recognition. Cultural values that prioritized celestial knowledge. Brilliant minds working within their available technology. What we've lost: modern civilization has sacrificed certain capabilities. Connection to the night sky, light pollution, multi-generational thinking, short-term focus, patient observation, demand for immediate results. Integration of astronomy with daily life. Technology does it for us. The inspiration: ancient astronomy should inspire us. Human capability is greater than we realize. Patient observation yields profound insights. Technology isn't necessary for sophisticated understanding. Ancient peoples were our intellectual equals. The challenge: can modern humans match ancient astronomers? Try observing the sky systematically for a year. Track a planet's position relative to background stars. Use only naked eyes and careful records. See if you can predict its future position. If this journey through ancient astronomical genius has shown you that our ancestors were far more sophisticated than we give them credit for, smash that like button and subscribe for more investigations into genuine ancient achievements. No aliens required. And here's my question for you: What impresses you more, that ancient peoples mapped the cosmos without telescopes, or that they had the patience to observe for centuries? Drop your answer in the comments. Hit that bell. Until then, go outside on a clear night, look up at the stars, and remember our ancestors looked at that same sky and figured out the universe's mechanics using nothing but their minds, their eyes, and their boundless patience. The cosmos didn't need aliens to be understood. It just needed humanity's greatest gift, curiosity.